Hello, everybody. I'm going to go through the solutions of the question 198 in the calculus section for the course Maths1151 at University of New South Wales. In this question, we would like to we have a level of surfaces of the form fxy is equal to 0. We would like to find the tangent planes and the normal lines to the surface at given points. So this is our level surface, and this is our point. I'm going to go through the solution for the part A and C only. The information or the theorem related to this question is following. So the tangent plane to the level surface fxy is equal, z is equal to k. At the given point x0, y0, z0, as the plane through that point with the normal of the gradient with gradient. This is this sign here, upside down triangle, is nabla del of f x0, y0, z0. Nabla f is defined as, which is the gradient, defined as this vector. So this is a vector form. Be careful, very careful. And if it is the gradient asked, if you're giving only the solutions like fx, fy, fz, it will be incorrect. It is a vector and it needs to be given the solution as a vector form. So the ijk, never forget that. It is there. Okay, what is this is the equation for the tangent plane. So fx, this is the partial derivation with respect to x, partial derivation with respect to y, and then that's the partial derivation with respect to z of this function. Then you are placing x0, y0, z0, and then x minus x0 and y minus y0, z minus z0. They're giving you the, these are the points, general position point, and so on. So this is this is a formula for the tangent plane. If you want to find out the normal line to the surface S, that basically this is the surface S is the given by level surfaces of this. Line through the point P is perpendicular to the tangent plane. And given by, so this is a line equation. So x minus x0, x is unknown, x0, y0, z0 are point. First derivative, derivation with partial derivation with respect to x, and evaluated at the point. That should be y here. There's an error there. This is y here. And so, and that's z, that's fz, and that's the gradient. Okay, only thing that we need to do just to calculate things and put it in. So let's do how to do the calculations going through. This is our function. So f, you would like to get this one is like you would like to take z on this side, or you would like to take all the others on the other side is equal to k. Right? f x, y, z is x plus y minus z, or equivalently, you could say minus x minus y plus k. It doesn't matter because you are thinking this function is equal to some values, and the values varies of this kind as a level surfaces. So it really doesn't matter which side it is. But you need to say when you first have this connection, then first we write it down our function big F. And the point is 1, 1, 2. We take the derivation with partial derivation with respect to x. We have 1. Partial derivation with respect to y. We have 1. Partial derivation with respect to z will be minus 1. Well, these are the constant functions. So it doesn't matter which point you are in. It's always that. For every point you have fx is equal to 1, fy is equal to 1. There is nothing to substitute. substitute. So it's very straightforward for this part of the question. So x minus x0 is 1, y0 is 1, and z0 is 2. So x minus x0, y minus y0, z minus z0. I need to show you the equation. So this is the equation that I am writing, which is the tangent plane of the surface. Fx is 1, fy is 1, fz is minus 1. Put it in, write it down. So this is the tangent plane at the point. So for the normal line, so that's the equation that we have, x0. So again, fx, this is a constant, which is 1. This is 1 constant for us, and this is minus 1 for us for this question. And x minus x0, which is x minus 1, y minus 1, z minus 2. And fx will be 1, fy is 1, fz is minus 1, is equal to lambda, or why I said lambda here, this is the constant action. You can, by writing down lambda, you can write it down. This is giving you a form of a normal line. If you want to find out the parametric form of that line, you can do so by letting this equation as lambda and get the x. X will be lambda plus 1, y will be lambda plus 2, z will be minus lambda plus 2. So the x, y, z is a position vector. And the point, the constant terms here, 1, 1, 2, 1, 1, 2, which is our point basically. Then you have the coefficients of lambda, which is 1, 1, minus 1. So this is the normal line, and that is the tangent plane for this question. Let's have a look at the other one. Now this one, depending on the point, partial derivatives depending on the point in this question. X squared plus y squared plus z is equal to 0. We are thinking f, x, y, z as a function x squared, y squared, z squared. And then first we looked at the partial derivatives with respect to the x, y, z, with respect to x to x, with respect to y, with respect to z, which is a constant function. Now you substitute this point here for x is equal to 1, that will be just 2. And y is equal to 0, that will be 0. Fz will be 1. So this is the equation, tangent line equation. So we have 2, x minus x0 is 1, fy is 0, and then y minus y0, which is 0, again 0. The whole of them will be 0. Then we have fz, which is 1, fz, z plus 1, z minus z0, z0 is minus 1, minus 1, minus 1, plus 1. So this is z plus 1. So tidy up this equation. We have 2x minus 1 here will go to the other side. And we have minus z minus 1 will go to the other side. Then we have minus 2 here, and we have minus 1 here, which is minus 3. So we have 2x minus z is equal to 3, which is the tangent plane at the point. Now for the normal line, here we have fy is equal to 0. That means that we are not going to account of this case. Only we are going to think x minus x0 over fx at the point, z minus z0 fz at that point. This is the normal line, and this is a Cartesian form, and we can turn into the parametric form by saying that this equation, this ratio is certain number, lambda, and then getting the x. So x is equal to 2 lambda plus 1, which is this one. Z is equal to lambda minus 1. Coefficient of the lambda which will be 2, 0, 1, because y will give you the 0. And then the y is equal to 0 in this case. And the constant terms here, 1, 0, minus 1. The constant term is this one, and the coefficients of lambda is this one. So this is the parametric form of the normal line, and this is the tangent plane at P. But it's pretty straightforward if you know exactly what to use, which theorem to use. That will be a straightforward calculation in that question. Thank you very much.